Hello everyone. In this video we are going to talk about forced vibrations of single degree of freedom system where the forcing function is an external force and that force is a harmonic force, is a sine or cosine. Like previous videos, the pictures and equations are coming from the book Theory of Vibrations with Applications by William Thomson et al. So let's get started. So here we start with the simple mass spring damper system with the harmonic force, assuming that there is no Coulombic friction under the tires rolling without slipping. Therefore, in the x direction, sum of the forces is going to be negative kx from the spring, negative cx dot from damper, and the external harmonic force that is equal to ma or mx double dot. Take all of the spring and damper force all to the one side and you get your governing ODE. Here we go. So now using the notations from previous lectures, calling square root k over m as omega n and c over 2 square root km as zeta, and also calling omega n square root 1 minus zeta squared omega d and zeta omega n as sigma, you know that this ODE is not homogeneous anymore. The right-hand side is not zero. Therefore, you have two parts to the solution, a homogeneous part and a particular part. The homogeneous part still is a basically damp harmonic if zeta is less than 1. If zeta is equal to 1 or bigger than 1, it's just decaying exponentials. So this part that I wrote that homogeneous is a damp harmonic, this is assuming that your zeta is less than 1. If zeta is bigger than or equal 1, then we have to use the solutions that I introduced in my previous lecture. Just go back and look at it. So this was for the overdamp response. And then for critically damp, this was the solution. Okay, so one of these will replace that x homogeneous. Now for the particular one, it will take the shape of the forcing function. So since your forcing function is sine omega t, then your particular solution will also be sine omega t, except with two changes. One, the amplitude of it will be modified. So instead of f naught, it will be x, and it will have a phase lag or lead, which you call phi. So it will have a modified amplitude and phase, but the frequency of it has to stay omega, and if it's sine, it's a sine. If it's cosine, it's a cosine, right? So you know that from differential equations. Now, in order to find this amplitude x and phase phi, we have to plug in the particular solution back into the differential equation. So we plug in the xp right into the ODE. And of course, we need to find the derivative first and second of this harmonic function. So first derivative and second derivative are shown here. We plug them in and you get this big of an equation. Now, if you look here, there are some terms that are sine, okay, which you can factor it out here. There is a cosine term, which is like the sine plus 90 degrees phase shift, and this is equal to a sine. Okay, and from here, the goal is to find x and to find the phase. Now, you can either use trigonometry equations and find it, or you can use this picture here that shows the system. So here, if you look, this direction, this phase is omega t, right? So this one, and the magnitude of it is f naught, then this vector here is actually your forcing function, right? That is this right-hand side that you have. Then, with a phase difference of phi, so phi behind omega t, so you have to move back in the clockwise direction by phi. In that direction, by magnitude x and multiply by k, you are going to have the force from the spring. So kx sine omega t minus phi is going to be this vector, assuming that k is bigger than 1, of course. Then, if you look in the opposite direction, because if you look here, the acceleration has a negative sign to it, and the amplitude is modified by omega squared, you are going to have multiplied by m, you are going to have the acceleration term, this guy here. And that is exactly what you see this vector for. This is m omega squared in the negative of x. And then what? You have the damper force. Now the damper force is the magnitude of it, if you look, is cx omega, but is cosine. And cosine of any angle can be written as sine of the angle plus 90 degrees. So I can write this as sine of omega t minus phi plus pi over 2. Therefore, it has an extra pi over 2, and this is what? This is that damper force. So you see that the mx double dot, this is that mx double dot, this is that cx dot, and sorry, this is the mx double dot, the one on the top, and this bottom one is kx. Sum of these three is equal to your external force F. So you see, you can show it with this pictogram. And now here, if you want to find phi or x, that's not really a hard thing to do. Why? Because you can use simple geometry here. So if I want to find phi, all I need to do is to form this triangle here, this right triangle, and find this magnitude, which is clearly k minus m omega squared, the whole thing times x. This is this side of it. The other side of it is c omega x. So I can say tangent of phi is c omega x over k minus m omega squared x. And the x's would cancel. So there we go. That is your phi here. That is your angle. And then if I want the magnitude, again, I can look at the same triangle. Again, if I square this one and add them together, it should be f naught squared, right? The Pythagorean theorem. And from there, I can see that x squared is going to be f squared divided by these two components, these two coefficients squared. And then once you take a square root, there we go. Look, you got the magnitude of x. So finding x and phi through this pictogram is the easiest thing you can do. Now, we can also write this magnitude function and phase function in terms of the damping factor and natural frequency. How? Here, we're going to divide everything by a k in numerator and denominator. Now, since the denominator has square roots, we have to divide by k squared. And if you simplify, you are going to get this. And once I have that, now here this m over k can be written as square root of m over k, and then if you take reciprocal, that's basically 1 over omega n squared. And here also, this part, you can write it as 2 zeta omega over omega n, because you know, if you simplify that, that is 2 times c, and this is 2 square root km, and this is omega, and then you have omega n, which is square root of k over m, right? You see the m's would cancel, and the 2's would cancel, and you get c omega over k, which is exactly this one. So you can write that portion as 2 zeta omega over omega n, this part as 1 minus omega over omega n squared, and then the whole thing, the added squared, and then under square root. So this is going to be your function in terms of natural frequency and damping factor, and of course the extra constant of f naught over k, which is basically your static deflection of the spring, right? So if statically you apply f naught, not f naught sine omega t, just the constant force f naught, then the spring will deflect by k so that the object is at equilibrium. So that is kind of like that. So for this one also, we divide again both numerator and denominator by k, and then again that is 2 zeta omega over omega n, and this is 1 minus omega over omega n squared. And if you see, these are these components, okay? So arctangent of that. Okay, so this is magnitude and phase functions. And 1 second, we want to look at their plots as this ratio omega over omega n, outside frequency or external frequency over natural frequency. When this ratio changes, we want to see what kind of curves we would get for different values of zeta. So what happens? Well, here, these are the curves that you can see. They are both omega over omega n in the x-axis and on the y-axis. For this one on the left, the ratio is x k over f naught, and here is just phi in degrees. Now you might say, why x k over f? Because they wanted to just plot 1 over this, so they multiply both sides by k over f naught so that this guy becomes a 1. Okay, so they want to plot this function 1 over that, not f naught over k. They don't want to bring in an extra set of parameters f naught and k and scale the whole thing up or down. So you see, this guy is only a function of zeta omega n. This one is only a function of zeta omega n. So what happens? Well, at omega over omega n equal 0, what happens to this curve? Well, if you look at it at 0, this is going to be 0, this is going to be 0, so you should get a 1. Regardless of zeta, the magnitude should be a 1 for all of the curves, and that's what you see here. It's 1 for all of the curves, okay? Then, when omega over omega n goes to infinity, your frequency of the excitation becomes very large. Clearly, it's in the denominator, so it should go to 0. And again, that's what you see for all of them happening. They are all converging to 0. Okay, now each one of this curve has a maximum point. Okay, you can see that except for xi is bigger than something, which we'll see what number. Except for xi is bigger than some number, all of these curves have some maximum point. And after some zeta, sorry, not xi, zeta, after some zeta, there is no maximum in the curve. We'll talk about that. So first thing is this maximum amplitude of the response of the system that happens, that is called resonance. Okay, so resonance is when you have the maximum response amplitude, and if you look at it, for most of them it is happening around the ratio of 1. 1 means what? 1 means omega over omega n is 1, or in other words, the outside excitation frequency is the same as what? Your natural frequency. So around the natural frequency of the system, if you excite the system with the same frequency, the amplitude of the system response will be large. And again, this phenomenon in vibrations, we call it resonance. And the thing is, at resonance, the energy that you're injecting into the system is injected at the exact time, at the best time. So the transfer of energy is done most efficiently. What does that mean? Well, probably if you had somebody on a swing, right? So you had some kid on a swing and you push them, correct? When your child is on a swing and you push them, so he goes forward, and then when the kid comes back, you push them again. Now, if you do this push at the right time, you are trying to inject the energy exactly when this pendulum is about to move forward. You inject the energy at the right time, so you accelerate the system. Now, if you do the push when the pendulum's still coming back and you do the push, what are you doing? You're slowing it down. So a portion of your energy is used to slow down the pendulum, then a little bit of the energy left is used to accelerate it forward. But if you wait until the pendulum comes here to stop by itself and then push it, you're using all of your energy to push the pendulum forward. So you see that the pendulum, or the swing in this case, goes further up because you are injecting the energy at the right system. And the frequency of injecting the energy or pushing is exactly matching the oscillation frequency of this pendulum, or the natural frequency of the pendulum. Okay, so this resonance, if it happens, it is going to cause the response of the system to be large. and it can have devastating effects in lots of mechanical or structural systems. Like when a shaft is spinning, it has natural frequencies, and you want to make sure that if the load that comes from the gears on the shaft is harmonic, then it is the frequency of that load is definitely way above the natural frequencies of the shafts, so you don't get a resonance in the shaft response. Or if you probably all have seen the Tacoma's Narrows Bridge, right? So if you just search YouTube, so this is that video, and this is one of the most famous videos. You see that's this huge bridge, very strong, but some wind that, as far as I remember, it was like only like 30 miles per hour or something. The wind was not strong, but the natural frequency of the wind was close to the natural frequency of the bridge, and the bridge supports for this torsional vibration. You see it is doing torsional vibration. It was not strong enough. They removed a lot of cross members, so the torsional stiffness and damping of the system was very low, and as a result, you see a small wind that would not otherwise damage the wind at all will make the bridge just basically dance like that, and then boom, falls down. Okay, so the wind was not really that strong, but it has the right frequency, and the system was not supported for, again, torsional vibrations. So this resonance can be very, very dangerous if it's not attenuated properly. So let's go back and look at this graph. You see that if zeta is 0, there is no damping in the system. Now that's theoretical. Any system has friction and internal damping. But if it's very, very small, what happens? How much is going to be the magnitude at the resonance frequency where omega equals omega n? What happens? You see that these curves are going to infinity. So you can have infinitely large response when there is no damping and omega equals omega n. So if you look at the magnitude, you see that when zeta is 0, this damping term is going to go away, and you're only down to here. And of course, when omega equals omega n, this whole thing will be 0. So you have number divided by 0, which will go to infinity. So clearly, you do not want to have your omega of the excitation to be the same as omega n when you have no damping. But when you do have damping in the system, and this term is not 0, still, when you are close to omega n, you will have some maxima, and this maxima could be relatively large if your zeta is small. So the first thing is, at what omega does this maximum happen? And well, if you know some simple calculus, you know you have to take derivative of that amplitude with respect to omega and set it to 0. If you do so, the omega that you will find is called the resonance frequency, and that resonance frequency is going to be omega n times square root 1 minus 2 zeta squared. So it's at this frequency where the maximum is happening. You see, it's close to omega n when zeta is very small, it's close to omega n, but the bigger the zeta, the smaller it gets. So omega r is less than omega n or equal for different zeta, and the bigger the zeta, the further it shifts to the left. And you can see that here. Look, this is the point of the peak, right? It was right at omega equal omega n, and the bigger the zeta becomes, you see, it is further shifting to the left. Okay, so that frequency here is omega n times square root 1 minus 2 zeta squared. That is that omega, or omega over omega n, if you want that ratio, then it is going to be simply this. Okay, so that is that ratio at that point where the maximum is happening. It's a function of zeta. And how much is the maximum at that point? So what is the maximum all you need is to plug that omega back into the X and find it. And if you do so, this is the maximum that you will find, which is called the resonance magnitude or the resonance peak value. And again, you see it's a function of zeta and of course F naught over K. So the actual maximum value is a function of zeta as well as the resonance frequency, and these are the formulas for them. And this is the plot of the peak value versus zeta, but the peak value is shown in decibels. So basically 10 log 10 of that is shown over here. And you see that, of course, it is dropping. As zeta gets bigger, M gonna go down. So more damping in the system means smaller resonances, and you clearly can see that, right? Look, you see the height of these resonance values drops as zeta gets bigger, and their point, their omega, is further shifting to the left. So this is the X plot. Now you see that there is no maximum in the X plot. If zeta passes some number, there is no maximum anymore, right? You see for zeta of 1, there is no peak. So after what value of zeta, you will not see any maximum anymore? Well, you see, if you go back and look at this formula, omega r can only be defined as long as under the square root is positive. And under the square root is positive as long as zeta is less than 1 over square root 2 or 0.707. Okay, so only for zeta between 0 and 707 is where you can have a peak, or actually this one less than. Only for this range you can have a peak, you can have resonance. After that, there is no peak. Your peak is just going to be 1. Okay, so if there is a limit for which there is some peak, that is going to be 0.707 or something a little bit less than that. You can have a peak and then the resonance will disappear. So this is for the X plot. Now for the phi, if you look at the phi plot, what kind of results are we supposed to get? When omega, again, is going to 0, or omega over omega n is going to 0, very small excitation frequencies, well, this is going to be 1, this is going to be 0, so you get tangent inverse of 0, which is 0. So all curves should start at 0. And when omega over omega n goes to infinity, you're having very, very large excitation frequencies. Well, since the denominator is order 2, numerator is order 1, so again, the whole ratio is going to go to 0, except with one difference. What is the difference? The difference is it is going to go to what? This number, if you simplify, this number is going to be very large, and when 1 is subtracted from that number, the numerator compared to denominator is going to be basically something like 0 divided by a negative number, instead of 0 divided by a positive number, which happened at omega to omega n go to 0. So when you're looking at something like this, the angle goes to 0. When you're looking at this, your angle is going to go to 180 degrees. And that is what you see for all of these curves. They are all converging to what? 180 degrees. So they all start from 0, go to 180. Another thing is what happens to them when omega equals omega n. So when omega over omega n equals 1, what's going to happen? Well, if you look back at the curve, when it's 1, this denominator becomes 0. The numerator becomes 2 zeta, and so number divided by zeta goes to infinity, and tangent inverse of infinity is 90 degrees. So all of these curves, regardless of zeta, they will all intersect at 0.1 and 90 degrees as well. Now, of course, the bigger the zeta is, the slower it is it takes it more time for the phase to go to 180. The smaller the phase is, the faster it is converging to 180. And again, that can be discussed as well. So this is your phase diagram. This is your magnitude diagram. So now that we taken care of the particular solution. We know what is x and we know what is phi. Now we need to look at the homogeneous solution. Now the homogeneous solution, again, as I said, depending on the zeta, bigger than, less than, or equal 0, it can have under, over, or critically damped response. So let's say, for instance, if it has under damped response, this is the response for it, and it has two unknown constants, A and B, right? The question is, what is A, what is B? How do we determine them? Well, of course, you have to use initial conditions. So we have to plug in the two initial conditions, x0 and x dot 0, and that should give us A and B. Now pay attention, when you want to find A and B, if you remember last time when we did find A and B, what did we do? We plugged into the homogeneous solution one time t of 0 for x, one time t of 0 for x dot, set them equal to this constant, and we found A and B. Good. But this time, your solution is not just homogeneous solution. If you want to plug in t of 0, in which one of these solutions would you plug in t of 0 and find A and B? You might say, do I still plug in t of 0 in this homogeneous solution, set it equal to x0 and x dot 0, and then find A and B? No, that is a big mistake. If you want to find A and B, you have to plug in t into the total solution. T of 0 should go here. So this particular solution will be involved as well. And then from there, you can find A and B. So if I want to just show you what's going to happen in this case, so x total at 0 is going to be what? So this sine term is 0, this cosine term still, this exponential there. So you're going to get B for the homogeneous, but for the particular solution, you're going to get x and then sine of negative phi. This thing here is equal to x naught. Do you see that? Okay, so this x is going to be there and this phi is going to be there. Now, are these constants? Yes, because they depend on, they are functions of the omega. And this omega is fixed for a fixed input. So these are just going to be fixed numbers. So from here, you can find B. And then when you do x dot at 0, again, remember, you have to take time derivative of this and this both. So the derivative of that, if you remember, there are two derivative terms. So you're going to get a negative sigma, correct, times the whole thing. So you're going to get negative sigma B. And then you are going to get a omega d, right? You're going to get plus a omega d. And that plus the portion of the particular solution, which is time derivative of sine omega, which is omega cosine omega. So you are going to get omega x cosine of omega t minus phi t 0. So you're going to get cosine of negative phi. This thing is going to be x dot 0. Do you see that? And again, remember, omega is a fixed number, phi is fixed number, x is fixed number, omega d is fixed, sigma is fixed. So once you find B from the top one, you can plug it into the bottom one and you can get A. So if I want to give you a solution, it is going to be B equals x0 and then plus magnitude x times sine of phi. And then you plug it down in the bottom one. A is going to be some big thing divided by omega d. Now, what is the big thing? It is going to be x dot 0 and then minus omega x cosine of phi and then plus sigma times B, and B is whatever I found up there, like this. Okay, so these are A and B. They are not just plugged into the homogeneous solution. And of course, I can add them here in front of my notes. So now that you have A and B with from initial conditions, and you have the particular solution, finally you can plot it. Okay. Now, if you plot that, this is the kind of response that you would get. This is your input. It's a perfect harmonic, magnitude 1, let's say. I simulated. I'll show you my simulations. So I used a omega n of, not omega n, omega. I used omega of 5 radians per second. My excitation frequency is 5. And my magnitude of the input is 1 Newton. And then in this system, my zeta is 0.25, my natural frequency is 10, and initial condition are 0.2 and 0.1. So if you see, the solution starts from 0.2, it has an initial negative, a small slope of positive 0.1, which is hard to see. You have to zoom into it. There is a small bump here that goes up and then starts dropping down. And if you look at your solution, you see there is a portion where the behavior is different than the rest of it. So there is a portion of the behavior that the signal is changing, and then after some time the signal is rather kind of constant magnitude, constant phase, and everything. So what happens? Well, in this time, the transient solution or the homogeneous solution, this portion, it goes to 0 because it has negative exponential. So this guy, as time gets bigger, this portion, this homogeneous solution will go to 0, whether it's a underdamp, overdamp, or critically damped, because they all have negative exponential, they will all go to 0. So this portion of the response that will disappear after a little bit time is what we call transient response. Okay? We can call the whole thing transient response, not just the homogeneous solution. So it's not really correct. Let me correct myself. It's not really correct to call only this portion transient. Transient is the whole thing. Okay? So transient is the whole thing where a portion of it is decaying fast and going away. So your signal is not stable, it's changing over time. So this portion is the transient response that goes away very fast. And then after some time, where that homogeneous solution goes away, you're only down to the particular solution, and particular solution is sustained oscillation with constant magnitude and constant phase. So that is what you can see after some time. This portion is called the steady state response. This is the response that, regardless of how much time gets bigger and bigger, this response will not change. Here you have a fixed magnitude x and a fixed phi. So here, half of this amplitude here, right, from here to here, this portion, that is your x. And then there is, of course, a phase shift between this signal and this signal, that is phi. Okay, and that is a function of all of these parameters. So that is what you can see, a little bit variability in this region, and then kind of steady behavior afterwards. And how long it takes, that all depends on the sigma. Okay, the bigger the magnitude of the sigma, the faster the transient response goes to 0, the homogeneous part of it, and it becomes stable and becomes like just pure steady state response. Okay, so if somebody says, what is transient response, what is the steady state response, you can answer. The portion that the homogeneous solution still exists is transient. The portion that is almost 0 and you're only down to the particular solution, that is your steady state response. And that is the part that stays regardless of how big the time can become. Okay, so this is a sample solution here. By the way, I made a MATLAB code for you that here simulates this same system for different zeta values, basically anywhere from close to 0 to 1 for this system, where C's are anywhere from 1 to 20, K is 10, M is 1, so natural frequency is 10, so C critical is 20, therefore here that number corresponds to zeta of 1. F is 1, there is no bias in the sine wave, there is no phase shift in the sine wave, and the range of frequencies that I pick for the excitation external force is anywhere from close to 0 to about 3 times omega n. My initial conditions are here. I use a large time to pass so I can get appropriate values for the magnitude of the particular solution. I use 200 seconds. And then what? Actually, I don't even need this portion. Then I use nested for loops. One of them goes from one zeta value to another, and then inside for each zeta, I go over all of the frequency values, because my goal is to generate basically this plot here. When you generate this plot, you need tons of data. You need a lot of frequencies, and each one of them has to be repeated for each zeta. So you need 2 nested for loops to get this simulation done. And that is exactly what I did over here. You see the result is very similar. If you put it side by side, I get a similar result. The reason there are these sharp points is because I don't have enough frequencies around 1. But you see the result is very similar to here. And you see these different zetas, these different ratios. So I could regenerate this plot for you basically by simulating a mass spring damper system, which you can see here, right? There is mass, there is C, there is K. Initial conditions will go here. That is for initial velocity. The next one is initial position. And then this is your external force, FB, omega, phi, and a sample time of 0.001 is used. So I made the transitions very smooth. It sends the data X and F to the workspace. And for each one of those omegas and each one of those zetas, I run my Simulink file. I get the T, I get the response, I get the input. And then what do? In order to get the amplitude X here, what I do is I only look at the last 20% of the time. So when I come and look at this solution, right, if my simulation runs for 10 seconds, I only look at the last 2 seconds of it. I only look at here. And from this point, I get the maximum, I get the minimum divided by 2 to get my X. Now, in this case, I run it for 200 seconds, so the last 20% is only the last 40 seconds of it. Okay, and if you want, you can change it to the last 10 seconds or anything. Just make sure this is long enough to capture 1 maximum and 1 minimum. And you see, that's what I do, divide by 2, and that gives me an amplitude. And then I'm gonna plot those amplitudes versus the frequencies. And then I go to the next zeta, I repeat that. For each one, I use a different color and I use a different label. And that is this beautiful graph that I got for you. Okay, but you need to run your MATLAB and Simulink, especially this M file, quite a bit long. I give you a download link for the Simulink and for the M file to run it if you want to regenerate this and basically use it for your vibration knowledge. So feel free to pass in any C value or any range of frequencies to this and get it to generate the magnitude plot. You can do similar things for phase plot. Here I just limited to magnitude plot for you, and you can learn from that. The last thing I want to talk about is called sharpness of resonance, or Q value, or quality value. So the Q value is defined as natural frequency, which is an approximation of the resonant frequency. These two are not the same. Remember, resonant frequency is this guy. So approximated here, divided by the bandwidth. And bandwidth is the difference between 2 frequencies here at which the signal magnitude drops to 1 over square root 2 of the max. So if this max here is 1 over 2 zeta, then by 0.707 of that, right, or 1 over square root 2 of that, which corresponds to 50% of the signal energy. Remember, the energy of the signal, if you looked at my previous video, that is proportional to magnitude squared. So if my magnitude drops to magnitude over square root 2, my energy will drop to the whole energy divided by 2, right? So energy will drop to initial energy divided by 2. So the energy of the signal drops by 50%, and that is where we define the bandwidth. So bandwidth is the range of frequency that the amplitude of the signal drops to 0.707. This range is called bandwidth, and these two frequencies are called the sidebands or cutoff frequencies, you might call them. Okay? 1T. And this distance between these two is bandwidth I have here. So if you divide omega n by the difference between those two, or the corresponding frequencies in hertz instead of radians per second, that is going to be Q value. And if you do it for the second order system, that is going to be approximated by 1/2 zeta. Okay, so you see Q value is a measure of sharpness of resonance. And what does that mean? Well, sharpness of the resonance, I mean, one resonance can look like this, one resonance can look like this. So this one has a sharper resonance than this one. What does it mean? It means your values increase very drastically, much more when you get to resonance than this one does. And this one is, of course, more dangerous because your system magnitude, the response of the system, increases very fast as you're increasing the excitation frequency closer to the natural frequency. This one, it takes a little bit more gentle approach, so this is not as dangerous as this one is. And of course, you can see that the Q factor is inversely proportional to zeta. So when damping is small in the system, the sharpness of resonance is bigger. And of course it is. Okay, because more damping, as we learned, more damping means what? Means smaller and kind of flatter plateaus here, as opposed to smaller zetas where you get these sharp resonances. Okay, so that is quite a bit obvious. And of course, a sharper resonance means faster or larger responses. They mean a long-lasting oscillations in the system, and they mean a basically at the same time lower energy loss, because when you have a smaller damping, of course you have smaller energy loss. Another way you can show Q, and I don't want to prove that, but you can show that Q is also equal to 2 pi times energy is stored in the system in one signal over energy dissipated per signal, per cycle. So of course, the smaller the zeta, the bigger the Q, and that means the bigger energy stored compared to energy dissipated, or basically the smaller energy loss. So hopefully this introduction to force vibrations of single DOF systems with damping with a harmonic external force was useful to you. Again, I'll give you a download link for the MATLAB code and for the Simulink file, so you can change the parameters and get different results if you want to. Thank you so much. I'll see you in the next lecture.